computer. Cool. Welcome everyone to another Less Wrong Weekly meetup. Welcome all 40-something of you. This week, instead of doing the normal lightning talks, we have one awesome talk by Scott Garrabrant. Scott Garrabrant's from MIRI. What to say about it? I really love the thing that Scott and Abram created, which is embedded agency. That was like one of the first times I ever felt I understood like what MIRI's research was really about. It like set out some key confusions, and then since then I've understood everything they've said and written much more. And then I'm really excited about this set of Cartesian frames, which is an interesting. I mean, Scott will say what it is far better than I, but I see it as an interesting formalism that seems to do much better according to the confusions laid out in embedded agency than some of the current competing ones. I don't know if there's anything else to say, except I'll keep admitting people to the waiting room. So Scott's going to chat now for somewhere around an hour. If you would like to ask questions during it, you can check the chat. Scott won't check the chat, but I will be in it. And if I deem a question worthwhile, I'll bring it up to Scott to chat about during the talk. Otherwise, there'll be Q&A afterwards for a few minutes, and then we'll be moving to the Less Wrong Walled Garden, which is a cool 2D space where you can walk around and chat with the people who are nearby you with Zoom-like calls, video calls. We'll go to Scott's office after that for more chatting. I think that's everything. Thanks for coming. It's going to be great. Looking forward to it. Other than that, I think I'll hand over to Scott, unless I've missed anything.
All right. Thank you. Yeah, part of the purpose of having a chat with questions is that there can be a low bar for asking questions. So ask questions and also maybe answer questions. Cool. So I'm going to talk about Cartesian frames, which is largely what I've been working on for the last almost a year. And this is, so the thing that I did immediately before starting to write up Cartesian frames was I would like come up with a like new model for how to like work with these specific things that I wanted to work with that are mostly like what I'll call controllables and observables. And Cartesian frames was something like the 20th iteration, at which point I was like, okay, now I need to just lock something in. And then I spent a long time writing and like going deep into a specific formalism. And then like once I stopped doing that, I then like went through and did more iterations, which is not to say that it's like old. It's to say that it's, yeah, I'm like still working with it, but like a lot of the stuff is fluid, and a lot of the stuff that's going into here is like going deep into like a formalism. I also want to say that this formalism, it wasn't just like the case that I was like, okay, I've changed the thing 20 times, let's like lock something down. It's like I actually expect that this formalism is going to at least be something that I can like compare future stuff to, and to be like a standard to compare to when I'm like playing with different ways of like playing with these concepts. Cool. This talk is, these slides are for like something like 3 hours of content. I'm not going to go through it all. I'm just going to go for about an hour and then go to do questions, and then I will give more of the talk in a week, probably. Yeah. Okay. So first I want to talk about some like conceptual parents to the thing I'm trying to build. First, there's there's Marcus Hooter's cybernetic agent model, or from wherever the model came from that we talked about in embedded agency, which is basically just you like have your AI interacting with an environment, and you have like messages being passed back and forth. The AI takes in observations, it like outputs, it has inputs and outputs, like takes in observations, like outputs actions, it like passes through time, and there's some interaction happening, and then eventually you get like an entire world history that is the result of this interaction over time. Another thing is Pearlian causality, which is, I don't know, causal graphs, DAGs. This is kind of like, yeah, you don't need to actually know what these things are. And then also game theory. The objects that I'm going to talk about are very much like games, but there's a sense in which the thing that I'm going to be doing is I'm going to be doing something that's similar to the spirit of Pearlian causality, where like you can interpret Pearlian causality as like there's this big joint distribution of how a bunch of variables are assigned, and this doesn't contain information about like the actual causal mechanisms. And then there's like a strategy to like infer the causal mechanisms by looking at the combinatorial properties of this big joint distribution. There's independencies in this joint distribution, and then you can like look at these. You can look at these, and you can use this to infer things like the time of what happened. And so roughly what I'm going to do is I'm going to take objects that look like they're coming from game theory, look like they're normal form matrices of games. I'm going to then use the combinatorics of these games to infer facts about things like inputs and outputs and time and stuff like that. And then be able to like recreate something that looks kind of like the cybernetic agent model, but has a lot of the things that were like just basically defined in the cybernetic agent model be more derived. Okay, so a Cartesian frame is a matrix. Really, it doesn't hurt at all to basically just be thinking about finite versions. I'm going to talk about it in cases where things could be infinite, but I think that like on a first read through, you should just assume finite so that you can imagine matrices. So we take a matrix and we have labels on the rows and columns. The rows of the matrix represent ways that your agent can be, and the columns of the matrix represent ways that the environment can be. So you can kind of think of this as like the different rows represent the way in which your agent can spend its free will. There's like this initial agent, there's like this agent A, and it has some choices, and each like way in which it can like do these choices is some way that it can be, which is represented by a row. And it also has some uncertainty over the environment. There are many different ways that the environment can be, which are represented by the columns. And then there's these W objects, which we'll call worlds, or maybe it's more accurate to call them world histories, which is basically just like the timeline of everything that happens. And so basically what you get is you have an agent, it has some free will, it also has some uncertainty over the environment, and if you combine a like possible way the agent can be with a possible way the environment can be, that kind of like defines the world history. Importantly, we will be working up to a kind of like macro level partition of the world history. So there might be like worlds that if you zoom in enough, they'd look different, but we're going to just call them the same anyway. And we're actually going to, like doing that is going to be important because we're actually going to be getting, useful work out of our notion of what worlds count as the same. Because the fact that we're calling some worlds the same is going to be what allows us to kind of get non-trivial combinatorial properties that we can infer things from. Yeah, so just, I will like call this A set the agent, I will call the E set the environment, and W is the world, and there's an evaluation function, dot, which is from A cross E to W. Yeah, so one way that you can think about this is like I've kind of drawn a Cartesian boundary in the world. I've said everything on this side of the boundary is the agent, everything on this side of the boundary is the environment, and the way that they combine, and then the two things combine. But you don't need to have like a physical interpretation like that, and part of the important part is that you don't. Yeah. Okay. So the thing that I'm going to do with this is I'm going to take this Cartesian frame object as like my basic thing. This agent doesn't have a notion of like inputs or outputs or anything like that. You can kind of think of the options as the outputs of the agent, but I'm not going to want to do that. I'm going to want to just think of it like there's the ways the agent can be, there's the ways the environment can be. There's no inputs, there's no outputs, there's no time. And then we're going to derive properties like that from the matrix itself. All right, so the easiest version is going to be outputs. I'm going to define insurables and controllables, which are kind of two different ways of looking at the outputs. So the insurables of a given Cartesian frame, C, is going to be the set of subsets of W such that the agent has some strategy that will ensure that the world definitely ends up, it's a set of subsets S such that the agent has some strategy that ensures that the world definitely ends up in S. So you have your agent and you just say, what are the facts that the agent can make sure to be true? So if you have an agent that has outputs, the outputs of the agent will count as insurables. Like the agent will be able to, assuming the agent actually exists, the agent will be able to ensure that it outputs a certain thing. Like it'll have the ability to ensure its own output. But it'll also be able to ensure things that are logical consequences of its output. So if you imagine an agent that's like sitting with a button and it can like press the red button and the green button, it can like ensure that it presses the red button, but also it can ensure that the red light turns on if the red button's like hooked up to a red light. And when I'm defining this insurable set, I'm putting both of those things in there, and I'm not I'm not like having an opinion on whether, I'm not having an opinion on like which one counts as the output, where to exactly draw the boundary of what's the output of the agent. Instead, I'm just like saying there's the things that it can make true. Those are all the insurables. So insurables is closed under supersets, which are like what I said with the logical consequences. If you can ensure a thing and there's a like set of worlds that's larger, then you can ensure the larger set also. And then we have another notion here, controllables, which is basically just like things that are both insurable and also their complement is insurable. So if the agent's like sitting in front of the red button and the green button, the agent not only can control whether it presses the red button, or can not only ensure that it presses the red button, it can also ensure that it doesn't press the red button. So whether or not the agent presses the red button is going to count as controllable, which is like you can ensure it and its complement.
Hey, Scott.
Yeah.
Can I just ask a few very simple questions from the chat?
Yep.
All right. The first one is, the difference between matrices and tables is that matrices can be multiplied. Is this just a table?
Yeah.
All right. Does each row AN represent a feature of agent behavior? Is it a feature of a state's actions or an internal state?
Yeah, so it can be both. Basically, you can have you can have like internal states, and it could be the case that the agent has some internal states that have no effect on the world, and then you might just have like multiple options in A that do the exact same thing as functions from E to W. Like you could have multiple like rows that look exactly the same, which might correspond to like I can like press the red button while like thinking I'm pressing the red button, or I could press the red button while thinking I'm pressing the green button, and these have the same effect on the world. And because I've like looked at like a macroscopic notion of the world that isn't actually looking inside the agent's head, and we could give those different rows, but also like it can have more meaningful stuff.
That makes sense. How much structure should I imagine W having? From the discussion of insurables, it seems like a lot.
Yeah, I'm not sure what you mean here. Like I'm only, W is like mathematically here just a set. Like I just like am taking, there's all the different ways that the world can be, all the different like possible world histories, and I'm taking some partition of them and I'm calling that W, and I'm like, it matters what partition I choose because I'll get like different results out of this. And so there's actually something that matters when I'm like saying, do these worlds count as the same? But I'm not going to be like explicitly assuming any structure, but facts about it are important. Yeah, I'm not sure. I'm not sure about what. I'm not sure if I answered the question.
Cool, thanks. We'll come back to maybe some more questions in a bit, but
Okay.
thanks.
Cool. Yeah, so these are my outputs. I can give some examples of these, but first I want to define this other thing, which is observables, which are like my inputs. So observables are also going to be a thing that you can like read off of the matrix associated with your agent, but they're going to be more complicated. Observability is going to, in this framework, mean the ability to implement conditional policies. So the thing that happens is, like, let's say I'm sitting here with like my red button, my green button, and there's also some input, some like letter pops up on the screen that's either A or B. And I can press the red button and I can press the green button, but also I could implement a policy that says press the red button if and only if the letter is A. And I can also, and also other policies. And the fact that I observe the letter is corresponding to my ability to implement conditional policies based on that letter. So the thing that's written here is, this is kind of the definition of a conditional policy. Yeah, this is like the definition of a conditional policy. If I have two rows in my matrix, and I have some subset of W, I could imagine a third row that kind of copies the first row if its value is in my subset S, and copies the second row if its value is not in the subset S. So it's like I have my two rows and I want to like introduce another one that just like copies this strategy in the S worlds and copies this strategy in the not S worlds. And observables are going to be subsets of S for which my Cartesian frame, my agent's actions, will be closed under being able to implement any conditional policies. And this is going to be closed under Boolean combinations, meaning that if I like observe one fact and I observe another fact, I also like observe their conjunction. All right. So this will make more sense if we go through some examples. So here's a basic example where you have an agent that is either going to carry an umbrella or not, and it is separately the environment is either going to rain or be sunny. So there are two possible choices for our agent and two possible choices for the environment, or two possible ways that the environment can be. And my worlds are just going to be the product of these two. There are just going to be 4 worlds that keeps track of, is the agent carrying the umbrella and is it raining? Okay, so here, the insurables, you can actually just look at these first 2 sets in insurable. The agent can ensure that it carries the umbrella, so it can ensure that we are in the world that contains UR and US. Those are the umbrella worlds. It can also ensure that it doesn't control the it can also ensure that it doesn't carry the umbrella. And then since insurables are closed under supersets, it can also ensure any larger set, any like weaker set. So these are sets of the worlds, subsets of W that the agent can force us to be in. And then the controllables are just these 2. So controllables are not closed under supersets. These are sets that the agent can both force us to be in and force us to not be in. And the observables are basically empty. You get for free that you observe the entire set and the empty set, because your conditional policies will be vacuous. So the agent doesn't get to know anything. In particular, it doesn't get to know whether or not it's, even though it is controlling whether or not it carries the umbrella, it does not get to know whether it carries the umbrella. Okay, here's another example. Here, our agent has 4 options because our agent is going to know whether or not it is raining. So the thing you can imagine here is the agent checks the weather channel and sees whether or not it's raining, and then can choose whether or not to carry an umbrella. And there are going to be 4 options. One is carry the umbrella. One is don't carry the umbrella. One is carry the umbrella if and only if it's raining. And the other one is don't carry the umbrella if and only if it's raining, or carry the umbrella if and only if it's sunny. And so in this case, so basically I tell this story in which the agent makes an observation and then chooses an action, but this story isn't actually written in this matrix. You can kind of see it in the labels maybe, but the matrix just says, oh, you have these 4 options, these 4 different policies that you can do. The insurables are now larger because it can ensure that it carries the umbrella if and only if it's raining. The controllables are also larger. It can ensure that it carries the umbrella, it can ensure that it doesn't carry the umbrella, and it can ensure that its umbrella-ness matches the rain or not. And then the observables now are going to be the agent. We have this partition, basically, where the agent can observe whether or not it is raining. So it can distinguish between, the agent can observe whether or not it is raining. The fact the agent can observe, so the set UR comma NR is the set of worlds in which it is raining. And that's what the agent is observing here. And then also the complement, the set of worlds in which it is sunny. The fact that the agent can observe whether or not it's raining can kind of be seen in that you can implement conditional policies. So, for example, there's a conditional policy that is, if we look back at our definition of conditional policy, it's if some set A0, otherwise A1. So if we take A0 to be carry the umbrella, and A1 to be don't carry the umbrella, this is saying that there should exist some row that copies the first row if we're in R, or if we're in a world in which it's raining, and copies the second row if we're in a world in which it's not raining. And indeed, the third row in the matrix is that conditional policy. Yeah. I just oversaw a question. I'm going to answer that question of like, why are these things subsets of W rather than subsets of E? Right? You can kind of think about the agent like observing some fact about the environment versus observing some fact about the world. It turns out that they really are kind of like subsets of E, and we're going to have a lemma later that'll like say that they're going to come from subsets of E. But I want them to be subsets of W so that I can kind of have them have the same kind of type as the things that I am have my observables have the same kind of type as my controllables.
Can I
also
ask 2 more questions? Sorry, do you want to finish answering that question if you're in the middle of it?
Yeah, you go to a question. I think I'm going to actually say more about that later.
2 other. I was about to jump in and ask that one, but thanks for answering it yourself. One question from David Mannheim, which is a bit more maybe philosophical. Maybe we come back to it at the end. Worlds are all possible worlds in the system. Can/should an agent be reasoning over which world they're in?
Yeah, I think that. Yeah, I think that I'm not thinking about the agent as being like in a world, or like I kind of am. Like an agent. Yeah, I'm not sure what reasoning means. Like the agent is like implementing conditional policies based on which world it's in. And this is like going to be like implemented via like internally in the agent. The agent is maybe reasoning about what world it's in and then like doing a different thing based on which world it's in. But I'm like not expressing that in the system. Yeah, I'm not sure how to answer the question.
Okay,
that's my
that seems fine. There is a math question about the definition of if. Rather than read it out, would you open the chat and just scroll up to user, I think psi, I can't remember the correct Greek letter.
Yeah, I think I'm going to get to that. I'm going to get to that soon. I'm going to put that off for now.
Cool. That'll do for now. Cool. We'll come back to more questions later. Thanks.
Yeah, so an important point here is that we can kind of look at these 4 actions, and we kind of think of like the first 2 as being like basic. And we can think about the second 2 as being like conditional policies, but that's just like our interpretation. And like the theory here is not going to actually distinguish between them. You could imagine another way of looking at the world where the world factors into, is it raining? And is our agent carrying an umbrella if and only if it's raining? And then our basic policies would be, yes, carry the umbrella if and only if it's raining, and no, do the opposite. But then you have these conditional policies, which are U and N up here, which like U represents carry the umbrella if and only if it's raining, if and only if it's raining. And I'm not like distinguishing between like what are like the basic actions of the agent and what are the conditional policies. I'm just like throwing them all together, and conditional policies is like a closure property on this set that's all thrown together. I'm going to give one more example, which is that now there's a third environment, which represents the Earth is hit by a meteor before the agent is ever born. So the agent doesn't do anything. You just have a world M corresponding to being hit by a meteor. The agent can ensure things. Here the agent has no control because it can't ensure any world not containing M, and it can't prevent any world containing M. And an interesting thing here is we're counting the agent as like observing whether or not the meteor hits, even though the agent doesn't exist in the worlds in which the meteor hits, or in some way of thinking about it, the agent doesn't exist in the world in which the meteor hits. And this is okay. It's like we're able to implement conditional policies because the conditional policies based on whether the meteor hits are going to be vacuous. Okay. So I'm now almost to the point where I'm going to answer this question, which maybe I should have repeated, which is like, basically my definition of if seems weird, my definition of conditional policies, because, and they give an example where the agent can do a conditional policy based on whether or not it carries the umbrella. And I was thinking about conditional policies based on things like, is it raining? So like, I don't know, there's a theme of questions here that's like, well, I'm defining conditional policies based on arbitrary subsets of worlds, but the kinds of worlds that are things that the agent is controlling, it feels like it's like less natural. And it seems like maybe I should just be defining conditional policies based on environments rather than based on worlds, because those are the kind of things that you can observe. And yeah, I'm about to get to that, but the answer is going to be that like you could do it with environments also, but I kind of want the environments to be less real than the worlds, and so I kind of want everything to ground out in terms of worlds. Okay. Here's our first theorem, or something theorem. The controllables and the observables are always going to be disjoint, assuming non-degenerate cases. So an agent cannot both control some fact and observe the same fact. Why might this be? Well, if the agent can control a fact and observe a fact, it will have some strategy that will, the fact that it can control the fact means it has some strategy that makes the fact true and some strategy which makes the fact false. The fact that it can observe the fact means that it can implement conditional policies. In particular, it can implement a conditional policy, make the fact true if you observe it to be false, and make the fact false if you observe it to be true. The agent will never be able to implement a conditional policy like this because a conditional policy like this is not going to be possible. And so the agent will not be able to simultaneously have control and observation over the same thing. And then I'm going to skip this. This is a similar definition in terms of insurables, and observables can't have to be disjoint or have to like not be too big, but we'll focus on the control version. So it's going to follow from this lemma, which will maybe explain the thing about conditional policies. If some set S is observable, then all of the columns have to entirely be inside S or outside of S. So observable facts will basically look like environments. So if you go back to this example where the agent could observe rain and sun, the fact that it could observe the set UR comma NR means that as a consequence of that, every column must be entirely in UR/NR or entirely out of UR/NR. So any observable fact has to be something that you can read off of the environment and is entirely not a function of the agent. So like we like define what it means for something to be observable in general, but it's like like a prerequisite for being observable is that you must entirely be a function of the environment. And the proof of this lemma is basically what I said before of like, if you have some environment that kind of goes both ways, you can construct a conditional policy that will kind of diagonalize against it and make it such that it's not like you can make it such that a conditional policy is kind of being diagonalized against and can't exist. You want to go questions, Ben?
My model is we have no questions at the current
Okay.
time. Please text me in chat if I made a mistake.
Okay. So yeah, so the answer to the E versus W question is that like we're basically going to be working with things that are coming from E, but we're still going to want to think about them as W. Okay. So we have these objects, which are these Cartesian frame objects, which you're thinking about as matrices. And now we're going to define a category with these objects and are going to have morphisms that correspond to functions in both directions. So the way that you can think about this is, well, I don't know, with the matrix, it's like you have your two matrices, C and D, and you have a function from the agent of C to the agent of D, and a backwards function from the environment of D to the environment of C. And these two functions have to basically like add up to the same thing. So if I'm given an agent from C and an environment from D, there's kind of two ways to combine them. One is to send the agent over to the D frame, and the other one is to send the environment over to the C frame. And both of those will combine to give you a world. And a morphism is a pair of functions in opposite directions, such that like you can compute the world either by going over to the C frame or by going over to the D frame, and you get the same thing. So a way that you can interpret these, morphisms is kind of like interfaces that allow one agent to play another agent's game. So you can imagine C, which is, so like C is the Cartesian frame that has our agent A, our hero, and then there's this other game that has an environment F and is kind of expecting an agent B. And so you can imagine this interface, which is some mechanism that takes in what the agent does and feeds it into the Cartesian frame that's looking for a B, and thus combines it with an F. So it's like a morphism is like a mechanism that allows an A to interact with an F, even though the F was kind of expecting a B and the A was expecting an E. This interface kind of translates between them to allow you to bring an A and an F together. So it allows one agent to like play the game of another agent. You can also think of the existence of morphisms as a kind of saying that one agent is stronger, in the sense of like, if there exists a morphism, it means that there's a mechanism for D's agent to basically strategy steal whatever C's agent would do. And so you get things like morphisms, like controllables and insurables are going to be monotonic on morphisms, for example. Okay. We have a duality here where we can take our category Cartesian frames and we can we have another category where we can like invert all the arrows, or I don't know, it's the same thing. I don't know. Basically, the thing the thing I just want to point out here is that if you have a Cartesian frame, which is a matrix, you can take the transpose of the matrix, and that gives you another Cartesian frame where you just like swap the agent in the environment. And part of the cool thing about this framework is going to be that like we're not going to have a meaningfully different thing for the agent in the environment. If you're thinking about these philosophically as the agent has some free will and the environment is like represented by uncertainty of the agent, then this duality is like actually doing something philosophically interesting. It's swapping like the free will of the agent with the uncertainty of the agent. So yeah, there's not a meaningful difference between the agent and environment. We can like swap them, and that just gives us another Cartesian frame that we can combine with other ones and such. Okay. So I want to introduce two operations that we can do on Cartesian frames right now. One is sum, which is basically, if I have two Cartesian frames, the sum of the Cartesian frames is basically an agent that gets to choose which game it wants to play. So the way that you can think about this is the agent, like the options available to the agent are the disjoint union of the options available to C and the options available to D. And the agent can basically choose which game it wants to play and then choose some option from that game. The environment has to choose a response. It has to choose a strategy for each game because it doesn't get to choose which game it plays. So it just like chooses what does it do in each game, and then you combine them as you would in whatever game actually gets played. Yeah.
Can I ask a few simple questions?
Cool.
Sure. I'll have a question, a comment, and then another question. A little before, Alibi asks, is there a useful weaker notion of sub-observable for things you can partially condition over, so that adding agents?
Yeah, I think that there's a lot of useful weakenings of observable. Yeah, so one example of a thing that feels partially observable, for example, is I have some agent and first I take an action, first I choose a number, and then I get to observe some letter, and then I choose a color. For the purpose of deciding the color, I get to know the letter. So the letter is partially observable by me, in that I can implement conditional policies on the part of my policy that's choosing the color, but I can't implement conditional policies on the part of my policy that's choosing the number. And so this is a way that you can formalize partial observability. And I will eventually get to this in the sequence where this is how to formalize time inside the Cartesian framework. But then there are other notions of partial observability. I don't formally do this, but there's a sense in which if you have a game, it's kind of like you are modeling two agents that both get to observe the conditional policy, that both get to observe the probabilistic policy of the other agent, but they only get continuous access to it, and so they can't do any function. They can only do continuous functions of the environment. And then there's also other things. I think that you should be thinking about this observable as the oh, and then there's also approximations to observability, where something's almost observable, but maybe there's little problems to it. And there's other things. You should be thinking about this observability as the gold standard of conditional policies, and then also there's all sorts of different notions of slightly weaker ways that you can implement conditional policies almost.
Cool, thanks. this is a comment that I just want to read from Sven in case you have any thoughts on it. They said that an agent can play the game of another agent is very interesting. Sounds a lot like avatars in Avatar logic, but I don't know whether it's the same thing.
Yeah, I don't know anything about avatar logic.
Cool, checks that. And then Mark Su's been chatting with David, and Mark Su said he'd be happy to turn on audio for a second and maybe summarize that, which might be interesting. I may have to turn on Mark Su's audio. Oh no, he did it. Go for it.
Yeah, so David asks this question, or is confused a little bit by why adding sort of rows to the matrix, which are like ways, adding more ways the agent can be, can actually reduce your set of observables. One way that this can happen is in the sort of rain umbrella example. If you added a new thing the agent could do that was like wear a raincoat, but you didn't add the ability of the agent to wear a raincoat if and only if rain, and wear a raincoat if and only if sunny, then you would no longer be able to count rain as one of your observables, because you couldn't condition this new action of wearing a raincoat on the rain.
Yeah, that's exactly right. Yeah, as defined here, observables is a closure property. Meaning that like you can add new things to your set, which cause it to like no longer be closed, but it's not actually making the agent any worse off, but like it's like making it no longer satisfy the closure property. Yep. Cool.
Yeah. Cool. Thanks, Matt.
Anything else?
Phi asked a similar question, as another follow-up question on if and obs. They write, it's difficult to grok if and obs. Can you reformulate if and obs somehow so that rather than quantifying overall actions, they quantify over atomic actions in contrast to composite actions or something like that?
Yes. Kind of. There's a thing where you could. Yeah, I think I might actually get to an answer to this question. We'll see. I think I'm not going to try to answer it now, but I might try to answer it in 2 slides.
Great, cool. That's all we've got for now. Thanks.
Okay, so I have a Cartesian frame 0, which is it has a singleton environment and an empty agent, which is like the identity of this sum operation. It's like you're adding an extra, you're adding like your disjoint unioning with an empty set of possible ways the agent can be. And you get the same thing. And this sum is going to be coproduct in our category that we introduced before. Here's an example, and it's basically like the actions available to the sum are the union of the actions available to the individual agents. The environments are the product of the environments, and they combine by basically you look at the row that tells you which of the components of the column to look at. You look at that component of the column, and that gives you the world from the matrix before. I'm not going to talk about this example very much because I'm going to go to another example after I define product, which is the dual to sums. Here, it's not that the agent gets to choose which game it wants to play. It's that the agent has to be ready to play either game. So the agent has to like give a response to what it would, a response of like what it would do in both the C game and the D game. And then the environment gets to like choose which game is being played. And this is exactly the same as before. We have top. Yeah, so this is, we use the ampersand symbol, and we have top, which is the identity of this guy, and everything is just dual to what it was before. So before we had like an agent gets to choose which game it wants to play, Now we have the environment gets to choose which of the two games it plays, and the agent basically gets to know the choice of what game is being played. So our example of this is going to be our example from before. So you can imagine the environment is, there's two different games. One is it's raining and the agent gets to choose whether to carry an umbrella. And the other one is it's sunny and the agent gets to choose whether or not it's carrying an umbrella. And then the product of these two Cartesian frames, like C ampersand D, is going to be the environment chooses which of the two games to play, and the agent gets to choose how it responds to each of those games. And so there's a sense in which, like, because we had, like, there's a sense in which, like, because of the fact that R was observable, that like UR comma NR was observable, that meant that we could actually kind of view our Cartesian frame as a product, which, like, there's a little bit swept under the rug there, which I'm not going to get to, but eventually, like, I'll have like alternative definitions of observability that will be able to be seen more as you can view your agent as a product of individual frames that are entirely inside and entirely outside of the set that you're observing. Yeah, I think that I now want to think about, yeah, can you restate the question I said I wanted to punt, Ben?
Yes, I can. Let me. Was it the one about if and obs?
Yeah.
If I wrote, it's difficult to grok if and obs. Can you reformulate if and obs somehow so that rather than quantifying overall actions, they quantify over atomic actions in contrast to composite actions, or something like that?
Yeah. Yeah, I think I actually am going to have to just like not really answer this. I think that the way to think about it is you have your set, I don't know, I'll give an answer. You have your set A, but you can kind of look at some partitions of A. So I have my set A here in my C5 and D5 matrix, but there's like a partition of A which corresponds to like what does the agent do in like raining worlds. And no, I think I'm just not going to answer the question. Sorry.
Cool, that seems fine. If Fire or others want to chat about that more, there'll be time in the walled garden after the talk to chat through some stuff.
Hold on, let me get one more. Wait.
There are two more questions I could ask.
My short answer is that you might be able to do something related to like not having atomic actions, but having like some higher grade, like some partition of actions that, yeah, I don't know. Never mind. Sorry. Next question.
I'll ask one more question, and then probably I'll let you just run through for a while, just to get through as much content as you like before the end.
Yep.
The other question was going to be, I think it was a simple one, Alex Menon. How should frames in which A or E is empty be interpreted?
They should be interpreted as they make the category nice, like to have identities for these operations. It's basically, one way you could interpret them is like, I don't know. The world doesn't exist, and there's a difference between the world doesn't exist and it's the agent's fault, and the world doesn't exist and it's the environment's fault. I don't know. I think that they mostly shouldn't be interpreted.
All right, cool. We'll call that a wrap on questions for a bit.
Cool. So sum and product are De Morgan dual, which I kind of already said. I think that I want to stop here, actually. So, yeah, maybe I should do, yeah, if there's any other questions or something that want to pop up that like thinks, yeah, I don't know. I will answer questions here until Ben tells me to go to Gathertown.
Okay. Are you sure? You could go for another 10 if you wanted to. Going through more slides.
I think that probably like my next chunk will take at least 15 minutes, and I want to stop after an hour.
Seems great. In that case, I will ask Gleb's question, which I just told him I wouldn't ask, which was, what happens when frames are misspecified? Like if you have a corrupted environment, if you have corrupted environment observations or incorrect belief sets.
I mean, mostly just like the formalism doesn't handle that, but there is a sense in which like I feel like I am trying to be able to do something like that. And the way in which I'm trying to be able to do something like that is that by making observations and controllables and such like derived properties rather than things that are like handed to you in the formulation of the problem, it's like setting it up such that we can kind of be more continuous and robust here, where we can like talk about things that are like almost inputs or things that are like almost outputs, or yeah, you could talk about things that are like almost inputs, where like it's like you have it as it's like it's almost like you're closed under conditional policies, except there are like some little things that are off about it, which I feel like by having inputs and outputs be derived, you kind of are setting yourself up to have more ability to talk about like slightly corrupted stuff that you still want to treat as inputs, even though they're a little bit off. But I'm not going to like explicitly do that.
Cool, thanks. Gherkin Glass asks, why introduce obs at all if it falls out of products for free?
It doesn't exactly fall out of products for free. For example, if I took this matrix, well, it doesn't exactly fall out of products for free. For example, if I took this matrix and I added one more row that's like, if I am carrying my umbrella regardless of whether or not it is raining, I also have the option of doing some internal thing that isn't going to show up in the world, and I'll just like copy the first row and have a fifth row that's the same as the first row. Like this thing still observes the fact, but it's not like legitimately going to be a product. As you can see by when you take a product, you multiply together the two agent sets, and it has a prime number of agents. That is like a prime, like the size of A is prime because it's 5. So we're going to work later. I don't know, this next section is all about like working up to deleting duplicate rows and columns. So in order to formalize observation as a product, you need to like first like understand what it means to like delete duplicate rows and columns. And then we could define observation that way. But actually, like the initial definition of being closed under conditional policies feels like philosophically an important thing to say about observation. And there are actually like lots of ways that you can define observation that give different philosophical interpretations. One of the posts that's coming in the sequence is like just like 8 definitions of observation, which I don't know, they're a little bit like packed, but there's at least like 4 very philosophically different interpretations of observation that like can cause you to think about it in different ways, which might be helpful.
Cool. Thanks. All right, I'm gonna say the next thing we're gonna do. There is at least one more question, but I think we'll move that to the walled garden. The next thing I would like to ask from everyone is I'm going to give you all a feedback form for this event because Scott's talk was well, we want to find out the truth about Scott's talk. So I'm going to give everyone a feedback form in the chat, and then I'm going to set a 90-second timer. It's very quick, and if everyone can fill that out, I'd really appreciate that. All right, there it is in chat. Let me know if you have any issues with that, and I'm setting a 90-second timer. And you have 30 seconds left. And time. All right, thank you very much. Appreciate everyone who filled that out, which was most of the people here. All right, I think we're going to move to the walled garden in a minute. Before then, Scott, do you want to say any things about what the rest of the sequence is going to look like and how people can continue engaging with it?
Yeah, I don't actually remember all the details. Is it? I think I'm giving. I don't know. Is it already set that I'm giving a talk a week from now? That'll be basically just like a continuation of this one.
That's right. That's going to be 2 hours later at 2 p.m.
Yeah, so 2 p.m. 1 week from today, I will basically jump in to continue with the next slide here.
And then, so the sequence is going to come out over the next, I think, 3 weeks. And at the end of each week, you're going to be in the walled garden, which I'm about to link everyone to. Next week to give a talk and do office hours. And then for next week's doing office hours as well, where anyone can come by and ask you any questions about this or share thoughts with you about this or who've just been reading along with the sequence, which is cool. And yeah, as we said, the post will come out over the next 3 weeks. Yep. And then otherwise, the next thing that's going to happen is if you'd like to continue chatting about this, all your participants, we're going to go to the walled garden, the Less Wrong walled garden. I'll briefly say what that is. So Less Wrong's been working on a space in Gathertown. Ray and Ruby have been taking the lead on that. It's a really cool looking place with lots of maps. You move around as a 2D avatar, and you go and chat with other people. Your video and audio comes on when you're within a certain range of other people. So if you turn up there, we're all going to go to Scott's office and continue chatting in a more freeform way, rather than just like one person on the podium and everyone listening. It'll be a bit more freeform, and that's in the walled garden. I also mentioned next week event, if you want to join in for that, it's going to be a town hall where I think me, Oliver Habrica, Divya Eden, Hannah Salomon, Zvi Moshevitz are going to chat about how Less Wrong in the rationality community have been dealing with COVID and sharing updates and taking questions. So you're welcome to come back for that next week. And And with that, I think I'll say thanks very much, Scott, for the talk. It was excellent. I'm continue to just be really super excited about this whole sequence. And now, if you'd like to go through to that link to GatherTown, I think people like Habrica and Ruby will be there to help guide people to Scott's office. I'll stay in the lesswrong.garden is also the correct URL. I'll stay in the Zoom call for a while in case anyone's confused or needs any help. But otherwise, look at all your people who've got no videos on. But otherwise, it's time to head over to lesswrong.garden. So yeah, thanks, Scott, and I'll see you over there.